Hi. I'm going to talk a little bit about experimental design. This is the first part of chapter one in your book. And we talked about this in class today on January 28th, our first day of class. So I want to make sure that those of you that couldn't make it to class today don't fall behind, but you'll find most of this material explained in the book. All right. So the first thing we talked about is what is critical thinking for scientists. That's part of what we want to learn in science is how do scientists learn and accept new knowledge. And so why would we believe something that a scientist says? The reason that I tend to believe scientists is because of the system for sharing information that scientists have. So, scientists don't just make claims and have everybody believe them based on how popular they are or how many books they sell or, who has the best Twitter account. What tends to be the case for the scientific community is that they have to publish in a peer-reviewed journal. So the editor of the journal will receive a copy of the experiment that was done, and they will critique it, and they may decide to reject this particular experiment. So why would they do that? We're going to talk after we talk about the why we might believe science about credibility. And so editors are going to be looking for some of these signs of whether or not a good experiment was run. Now, if it seems like everything's on the up and up, and it's an interesting topic that they think their readers of the journal may be interested in, then they will send that on to other scientists. And they're not just going to pick random scientists. They're going to pick scientists that are specialists in the same field. So if your study was about nutrition and children, they're going to look at send your article to other scientists who deal with nutrition and children. And the more specific your topic is, the more they're going to try and make sure that other people are going to be knowledgeable about that. So that's kind of the first thing, is that your experimental design is going to be critiqued, and people who know about that field, who are apt to be able to see signs of, you know what, you're making claims that aren't true, or you're basing that on an assumption that was debunked, they're going to be your first stopgap there to preventing bad science from getting through. So we don't just accept science because somebody, posts it on a social media feed or even just puts it on a website. They have to go through a peer-reviewed journal. Now, the people who receive this, they also have the option of saying, hey, looks great, go ahead and publish, which very rarely happens. Often what it happens is they say, I really think you need to fix these things. But they also have the option of saying, no, this is bad science. We should not publish this. And then once the article is published, other scientists are going to read this, and they are also going to be critiquing it. So anybody with any knowledge in the field is probably going to read the article, and they're going to be there to say, you use that formula in the wrong way. This only applies to this particular situation. And they're going to make sure that author knows where if they have made mistakes. And then the article usually is fine. But if there are problems, it might be redacted, or they might say, oh, I have to take back what I said because it was poorly executed. So these are the reasons why I tend to find scientists very credible. Dr. Fauci says this is what we've discovered about this virus. So I believe Dr. Fauci because I know that scientists are under this pressure to have things credible for this peer review process. Now, that being said, scientists have not always been good stewards of the public trust. So initially, science was mingled together with what was called natural philosophy, and that also included because people just did not understand some ways that the natural world worked. Natural philosophy might also include the idea of ghosts and spirits, which we would not put in science anymore. Resurrection, some other phenomena that we might consider paranormal, those would also be considered in the natural philosophy. And so as scientists were able to identify things that could be experimented on according to the scientific method, those two parted ways. Now, the other thing that has made scientists not always trustworthy is how experimentation has been done on people. So it's only been since the 1970s that we in this country have had laws that have stated that anybody who is experimented on must be autonomous. So that means they have to be somebody who can think for themselves and is in control of their own fate. So it can't be somebody who's like a prisoner who would maybe be influenced by promises of getting out of jail or promises of more time outside. And it can't be somebody like a child who isn't old enough to speak for themselves, or maybe somebody who has some sort of mental disability who maybe can't process the information. And it also says that they have to be informed. So you might have heard the term informed consent. And so we have to let people know what the study is about. We can't lie to them about the nature of the experiment within reason. And, we can't lie to them about how the results will be used. We can't lie to them about what the possible effects are. And then furthermore, we can't experiment on people with things that we believe may cause them harm. So, for example, you might want to see whether somebody who has brain surgery gets better because of the brain surgery, or just because they think, oh, you did something, it must be getting better. That's what's called the placebo effect. But it would be considered unethical to perform an experiment where you had a bunch of people who actually got brain surgery and a bunch of people who you cut open their brains and then just seal them back up again without doing anything, because that could potentially cause them harm, having the surgery, having their brain exposed to the air and all of those things. And so we wouldn't do that type of experiment. And there are some examples in your book of things that were considered, no, this just isn't appropriate for how we should do science. Unfortunately, and this is often the case, the people who were usually harmed by these lapses in ethical decision-making were often those in the most vulnerable populations. Children in orphanages who didn't have adults to speak for them. As I mentioned before, prisoners have often been subjects of experiments. You may also have the very poor or people of color that tend to be falling into those groups that were experimented on without either autonomy or consent, or both of them. So there is a past for science, and one would hope that it is mostly in the past, that has made some people skeptical of science. And so that's just food for thought to keep in mind why some people are very pro-science and some people are less so. What we're going to talk about is how scientists know what they know. So how do we know, and how well do we know it? In different subject areas and different disciplines, the way that you know things relies on different sets of criteria. The way you learn things in history is to go to primary sources, things that were written at the time, things that were written by the people that you're studying. But with science, we have different sets of criteria. Now, you've probably all know or have studied the scientific method. So I'm not going to go piece by piece through that. But we usually start with a problem, and then we want to address that problem, so we come up with a hypothesis. So a hypothesis, almost everybody will tell you, is an educated guess. Now, this isn't just a random guess. So it's not like, my car's not working. That's probably because I had oatmeal for breakfast. That would be kind of a random guess. A more educated guess would be, I know my car requires gas in order for it to function. Maybe it's not working because I don't have enough gasoline. So little bit of background on there, but we may or may not have ever tested this before. So this isn't, a hypothesis isn't something that would be published or accepted as scientific fact. It would just be a starting point for an experiment. Now, you may also have heard of a scientific theory. A theory ties together lots of experiments. So once lots of experiments have been done, scientists will look for the common themes and say, how can I explain all of these things that are going on in this experiment? What would be the cause of all of these things coming together? So a theory is an explanation, and it's based on many, many trials by many scientists. So a theory is never the result of just one experiment, and it's never a result of just one scientist's experiments. And in general, most scientists agree with this, but we don't necessarily have 100% agreement on it. There can be very legitimate scientists who look at a theory and say, I think you're missing something. I don't quite buy into the way you're explaining this particular aspect of something. So we do get a little bit of disagreement, and there's some debate on those things. And throughout history, even things that are mostly accepted today, when they were first proposed as theories, were debated quite a bit. So a law is going back to having done our experiment and seeing what happened. It just states this is what happens. It doesn't explain why it happens. There's no explanation. But laws are considered to be universally true. So we have the law of gravity, which basically says any two objects that have mass are going to be attracted to one another. And every scientist is going to agree that, yes, our observation has been that if two objects have mass, they will be attracted to one another. But it doesn't tell us why they're attracted to one another. It just says they are attracted to one another. So while it is universally accepted and there are no known exceptions to it, it doesn't explain it. So we might have a little bit of a difference in our certainty there, but also a little bit of difference in how valuable that is based on what it can explain. Now, neither of these cases do we have proof. And scientists sometimes will throw that word around a little bit too cavalierly, but we don't really prove things in science. We collect evidence, we support a claim, but there's always something out there that could possibly be part of the story that we don't know about. So if we think back to scientists trying to explain lightning 500 years ago, electricity wasn't understood. So they couldn't prove anything because nobody had really understood what electricity was. And similarly, we don't know right now what we don't know. So we don't necessarily prove anything 100%. But we have a lot of supporting evidence from a lot of different trials and a lot of different scientists who have both conducted experiments and reviewed those experiments. And then the last thing I wanted to talk about is a model. I heard an explanation one time for a model as a lie we tell ourselves to help us understand. So models never represent what is really models are never what is really going on. They are representations or analogies. So one of the analogies that we use in chemistry is we say an atom is like the solar system. So We have the center of an atom as a nucleus, the center of a solar system is the sun. Planets revolve around the sun. Electrons revolve around the nucleus of an atom. But we all know that a solar system, which is very, very big, is not the same thing as an atom. Okay, they are just representations, and the similarities between them can help us to understand what's going on with the atom. Okay, and that's an important distinction to make because sometimes we get kind of caught up in the analogy or in the model, the analogy or the model, and start talking about that analogy as if that's what's really happening, rather than it being something that's there to help us understand.